I'll be talking about X-rays mainly within SEM today. I'm not going to touch on anything related to TM. So what I thought we'll do today is we'll quickly review the theory of electron-excited X-ray production, and then we will see how we can apply this to the more traditional EDS analysis to obtain identification of your minerals just by simply pointing and shooting at an electron image. And after that, we'll be looking at a few mapping examples. After that, we will review some recent advances, particularly automated mineralogy, which is an interpretative EDS mapping tool. And at the end, we will review advances related to actually making quantitative analysis using EDX. And I'm writing EDX here and writing EDS over here to remind me of the next slide, which is that these acronyms are exactly the same. EDS is energy dispersive spectrometry, which is the same as EDX, energy dispersive X-ray spectrometry. Oliver already introduced you this great resource located, created by the Australian microscopy community. I've taken a few of my slides from the EDS module that they have. And for quantitative EDS analysis, I can recommend this review article by two of the main driving forces of using EDS as a quantitative microanalysis tool. This should be an open access PDF. And if you have any advanced questions, I recommend that you visit the forum located at the Probe software website, which is where all the gurus of this world will be happy to assist you with any challenges that you throw at them. Okay. So Oliver already showed this very schematic sketch what happens if you have a high voltage primary electron beam and you let that those electrons interact with your sample. You get all sorts of signals. The samples can be elastically scattered within the sample as a result of the interaction with the nucleus. And in some cases, those changes in the pathway can lead to a fraction of the electrons coming back out of the sample again. Okay, there could also be elastic scattering. In some cases, if the sample is very thin, there's no scattering at all. There are signals that we can use to image the materials that we're looking at. So we get these backscattered electrons. Secondary electrons tell us something about the morphology. Okay, and there are other signals that we're not going to go into today. But particularly the X-rays are signals that we can use to obtain chemical information. Also similar to what Ollie showed, secondary electrons from morphology, backscattered electrons tell us something about the composition. So we're looking at two slices, two images of the same material. This is a copper aluminum grid, and backscattered electron image shows us a bright area, which is the copper. It has a higher atomic number than aluminum, so larger fractions of the electrons re-emerge to the surface and are collected by the detector. That's why they are brighter in this image. At the bottom, the secondary electron image shows us the morphology of the sample, and it shows us that the copper grid is higher than the aluminum substrate. If we apply this to a real sample like this meteorite, we see that this backscattered electron shows us different minerals, different phases, a very bright high atomic number phase in white, or it could be more than one, which is surrounded by a medium gray phase and a big dark lower atomic number material, which is compositionally zoned, which has high atomic number elements at the edge, and more darker atomic number elements in the interior. And there is black material, so there are more than just 3 phases. Okay, and this is something that we get from very quickly getting a backscatter electron information. When we then get X-ray information and obtain the distribution of X-rays from iron and sulfur in this case, we see that there are intensity variations. And these intensity variations are typically displayed in these rainbow maps, where the darker colors, the colder colors, represent low intensity, and the warm red colors mean that there is a lot of iron in this case present. But for the same area, there is no sulfur present. So we can very clearly see that there's a strongly different mineralogy. Zone phase in this case shows that the low iron in the interior is complemented by high manganese. And darker little dots that show up as black in the backscatter image are enriched in the element magnesium. The time scale to obtain this information is very different. For the backscatter image, we can get a good image in less than 30 seconds. For an X-ray map, in this case, it was done with an electron microprobe. It takes up to several hours to obtain this, and if you want to resolve very fine details. So how do we produce these X-rays? This is a Rutherford Bohr model of an atom, where you have the protons and the neutrons in the nucleus, and the orbiting electrons in the various K, L, M, and N shells around the nucleus. When we bombard a sample with electrons at high voltage, those electrons are able to knock out electrons from the orbiting shells. So in this case, in the sketch, it shows that there's an electron from the K shell that is removed. So you end up with a temporary charge imbalance and a void. And that void is then replaced by an outer shell, in this case an L shell electron, taking a place in a more energetically favorable position closer to the nucleus. And that transition has a very discrete energy transition, and it leads to the emission of a photon that has the wavelength of an X-ray. But there are other transitions, energy transitions possible. And if we look at the nomenclature in the traditional sense, we call these K alphas, K betas, or L alphas. When you have an L shell to K transition, a K shell transition, that's K alpha. But if there's an M shell electron that goes and fills the void, then it's called a K beta. If you remove an L shell electron and you replace it with an M shell electron, then that leads to the emission of a photon called an L alpha, okay, and so on. There are many more that are possible, but these are the most common ones. And they have very distinctive energies. In the example of silicon in here, you can see that the K alpha and the K beta have slightly different energies. And the L alpha, if you remove this electron and you replace it with an M shell, that energy is much, much lower. If we look at a different element, in this case calcium, it has a higher atomic number, and its energies, although they are the same, K alpha, K beta, L alpha, they have higher absolute values compared to silicon. Okay, so these are called characteristic X-rays because they're element specific and their energy increases systematically as a function of atomic number. And there's a relationship proportional to the atomic number squared. There is another type of X-ray that you obtain when you bombard your material with electrons, and that is the so-called Continuum, also known as Bremsstrahlung, which is a German word meaning breaking radiation. And that is causing a background noise that we need to subtract from the characteristic X-ray signal in order to obtain a quantitative composition. So this continuum works as follows. The electrons are gradually slowed down within the material that you're shooting them at by the interaction with the outer shell electrons. Okay, and that leads to the emission of photons in a range of X-rays. So the measured continuum distribution looks like this whale shape. And the maximum energy, which we, by the way, express in electron volts or kilo electron volts, cannot be higher than the so-called Duane-Hunt limit, which is the accelerating voltage that is used to accelerate the electrons down the column. And for SEM, that is typically in the range of 10 to 20 keV. So in our experiments, we typically measure a mixture of the continuum and the characteristic X-rays, and then we get a shape, a distribution like this. If we apply this to in the most traditional sense, let's have a look at a few examples of the point-and-shoot analysis. So you first start by taking an inventory of the minerals that are present in the material that you're studying. So in this case, we're looking at a backscatter image where you have a number of bright phases and slightly medium gray, and then there are some darker phases, and maybe there are some slightly different phases. So the modern EDS software allows you to transfer the image that you take, or you take control of the SEM, and it acquires an image like this in a few seconds, and then you can click anywhere on the image to obtain an X-ray spectrum. And in this case, we're looking at the darker phase, and the 10-second or a 30-second analysis produces an X-ray spectrum with energy on the x-axis and the counts per second per electron volt, so the intensity on the y-axis. And most software is very user-friendly. It automatically labels the different X-ray energies that are present, or it comes up with suggestions at least. And you can see that there are a lot of oxygen, there's sodium, aluminum, and silicon. Okay, and you need to know a little bit about your sample to know what to expect and check whether the observation makes sense with your analysis. So in this case, this is an albite. And then you go to the next material, which is this small needle-shaped material, and you see that there's a big phosphorus peak and a calcium peak, a little bit of fluorine. So this is a fluorine apatite. So you keep going on until you have identified all the phases that are present. By the way, in the example that I showed earlier, here you can see all three of the calcium peaks. There's the K alpha of calcium, the K beta, which always has a lower intensity, and those ratios are between K alpha and K beta are more or less constant. So they contribute to this characteristic signature of an element. And down here at the very low energy, you get the calcium L alpha. An example of a traditional EDS type of mapping is shown in this slide, where I did a quick map of a Faraday cup. Okay, the backscatter image shows that there are three distinctive materials: a low atomic number element phase in here. The aperture is very bright, so that has a high atomic number, and it's held together with a spring that is medium gray in the backscatter image. So in terms of its atomic number, somewhere between this and that one. Okay, so then you get the element map that takes maybe 5 minutes or 10 minutes, depending on how much details you want to resolve. And you also obtain a so-called sum spectrum, so the total X-ray distribution of all the materials that are present in the image. And you see that there's aluminum present, there's molybdenum, and there's copper. Those are the main elements. Any modern software now allows you to overlay the distribution of these three elements. So we see then that we have a molybdenum aperture with a hole in it to measure the current for this Faraday cup. This is a copper spring that holds the plate, this molybdenum plate, in its aluminum housing. Okay, not very exciting, but it shows how, in principle, this works. If we move on to another example, this is a lava from Iceland, and we're going to zoom into this small area where there is a small alteration crust that is formed on top of the fresh lava. So the fresh lava ends here, and then you got all these different layers that are deposited on a scale of maybe 50 microns on top of the lava. So we did an element map on this with the SEM, and the SEM allows us to obtain all the elements that are present at the same time. And I've highlighted 4 of the elements in this slide. So we see that there's a silicon variation. Bright means that there's a lot of silicon. Dark means that there is none. So these little dots mean that there is no silicon present. You get a little manganese-rich rim. But the interesting part for the researchers that were part of this project was the distribution of copper. And because copper apparently plays a role in is bacterially assisted precipitation. So it's very exciting findings here. And we found even that there are these tiny little silicon-free copper phosphates. That was a very unexpected finding. So it illustrates that EDS mapping is a very visual tool that was also great for teaching, and with the modern software allows us to become much more user-friendly and faster acquisition if you have high-intensity detectors, and you have the potential to resolve chemical heterogeneities and things that are not obvious just from looking at the backscatter image alone. Okay, so if we then move on to a recent progress, is if you take this a little bit further. There's a software module called Automated Mineralogy that has been integrated on the Zeiss SEMs, and it was originally designed for ore mining and ore mining prospecting industry in order to assess whether the ore that they're recovering still has enough of a certain element of interest. Okay, so and we've applied this to a metamorphic or other standard basic research applications. So in the following, I have a few slides that are from the master's thesis of Hans van Melick, and he looked at metamorphic rocks from northeastern Spain. And he was kind enough to let me borrow some of his slides. So what you see in this slide is an optical micrograph with cross polars and linear polarized lines, and overlain on that is a mineral distribution map where each color represent a distinctively a different mineral. And that was obtained by using automated mineralogy and acquiring EDS maps. So it has converted X-ray maps into phase maps. We have done this with 2 spectrometers simultaneously, so that allows us to acquire these maps really quite quickly. How does this work? You start by, of course, getting a good sense of the minerals that are available. So you need to make your traditional point-and-shoot mineral inventory to assess the different minerals that are present. And then you collect grid-wise a different EDS maps that are at the end stitched into one big map. And for every grid, for every tile in the grid, you get a number of pixels, and for each pixel, you have a phase classification. Okay, and this phase classification is based on the library that you need to create as a user. So in this example, it shows the code that is part of the library. So I'm showing the definition of what is an orthoclase, a potassium feldspar. So the pixel needs to fulfill all these criteria. The software, the EDS software, provides you with a quantitative composition, approximate quantitative composition. And if your pixel fulfills all these criteria, it's labeled as orthoclase. If it's not, the software goes down the list to the next phase, and it keeps on searching until it has labeled all these individual pixels inside the tile. And then it moves on to the next tile. Okay, so this is something that you need to train the software. So you do the acquisition, which can take a day or, depending on the details, 2 days. And then there's a lot of post-processing adjustments to the mineral classifications. So Hans shows 3 examples, 3 iterations that lead to what he thinks at the end is the good result. But there are a few very tricky steps where you have a lot of this phase called MS, which is muscovite, a mica, which looks very similar to the potassium feldspar. So you need to look very carefully at the mineral recipes in order to reconstruct your final phase distribution image. And if you only look at the optical mineralogy image, this is something that is impossible to obtain. And I also want to say that this is also impossible to extract by using the traditional EDS mapping, particularly in this case because the muscovite and the orthoclase have such similar elemental variations. Okay, so we are very excited by the new avenues that this software module opens for our research. Okay, so then the last thing I want to talk about today, which is quantitative EDS. And I have a background of electron microprobe analysis, and I always thought that it's impossible to get quantitative, reliable mineral compositions using EDS only. And I no longer think that this is an oxymoron, mainly because of the work that Newberry and Nicholas Ritchie have done in the past couple of years. But there are a few requirements. The first requirement is that the software comes up with the correct peak identification. And every day there are so many, no, not so many, it happens that the software provides a wrong identification of an element that is present. Okay, sometimes it's worse, sometimes it's easy, but all the software still suffers from these problems. Then there are artifacts that need to be treated carefully. The most common ones are pulse pileup, which you get at high count rate. The high count rate is something that you want to use to get the analysis done as quickly as possible, but it leads to this artifact that we will look into in a minute. And then there are interferences that need to be dealt with. Okay, so let's quickly look at these. Pulse pileup is a dead time artifact. And dead time artifact happens when you have high count rates, when pulses arrive simultaneously and the detector is not able to distinguish these pulses. Okay, so in this example, 2 calcium K alphas that arrive at the same time can look, and they have this energy, separate energy of 3.8 keV. If they arrive at the same time, then the detector thinks that this is one pulse of 7.6 keV, and it could interfere with another element that is present at this energy. Okay, so the modern software is able to deal with these artifacts called sum peaks or pulse pileup peaks. But when you are looking at trace elements or lower abundance element elements that suffer from these pulse pileup effects, then you need to evaluate very carefully whether this is not causing artifacts to your measurements. Spectral interferences, and it's not only a problem for quantitative EDS, also for qualitative EDS. So this is an extreme case. So for this particular energy of 2.3 keV, you can have simultaneously sulfur K alpha photons present and molybdenum L alphas or lead M alphas, and they all arrive at the same X-ray energy. Okay, so when you think that is happening, then you need to deconvolve your spectrum. And in this example, Newberry and Ritchie have succeeded or have demonstrated that they're able to separate these peaks by deconvolving them, by stripping them, and ending up with the so-called residual, which is the background noise, by subtracting the relative proportion of both molybdenum and sulfur. How it works in detail, you can read in this article. One of the most important things that impede good quantitative analysis is the geometry of the sample. The sample needs to be horizontal and it needs to be well polished. And the reason for that has to do with X-ray absorption and fluorescence. And this is corrected for by any software, but it requires knowledge of the path lengths, which is the length that the X-rays travel through in the solid material in the region where they're generated to the spectrometer that collects the X-rays. And since we haven't talked about absorption and fluorescence, let's review this very quickly. So let's look at iron. When we bombard iron with electrons, you can produce iron K alpha X-rays. And these iron K alpha X-rays are traveling to the detector, but they need to go through the solid material from which they are generated. Okay. If there are other atoms present, like a copper, then these iron K alpha X-rays, they are able to knock out K-shell electrons from chromium and produce chromium K alpha. The iron K alpha is used to knock out a K-shell electron from chromium, so this photon is gone. In addition, we get this extra chromium K alpha that is also generated directly by the excitation from the electron beam. All right, so in summary, when you have iron K alphas that are used up by the neighboring chromium atoms, that is called absorption, and it lowers the intensity of iron K alpha that arrives at the detector. And then chromium K alpha is produced directly by the electron beam, but in addition, it can be produced by interacting with the iron K alpha atoms that are causing the chromium to fluoresce. Okay, and in the software, there are corrections that are necessary, and they're typically treated as a black box, but it requires that the geometry of the path lengths is known. Okay, so in the sketch, we're producing these electrons below the sampled surface, And in the ideal case, we have a horizontal surface. These X-rays, they need to travel to the detector. Okay, and on their way to the detector, they have this interaction path lengths where you can get fluorescence and absorption. If you have a tilted sample or a poorly polished sample or a regular sample, then this path length is different. And the absorption fluorescence correction is inaccurate. Okay, and if you have more than one spectrometer, such as in a multi-collector system like an EPMA, then you have orientation effects that can have this effect on one spectrometer, but not on another spectrometer. So it makes it very tricky. Okay, so then the last point, if you want to get quantitative analysis, you cannot rely on the standardless calibration-free quantification that comes with the factory settings of your EDS system. You need to calibrate with known standards, just like for electron microprobe analysis. And the very last point, to convince yourself that you have produced good results, is to measure external standards and publish those external standards along with the unknown compositions of your own samples. And I think this is where I'm going to end today. So I'll be happy to take your questions.